Shall we begin?
Yeah, okay. I'm not going to be there already.
Okay, good evening. Our today's speaker is Ian Marshall from High School of Economy, and he will speak about angle action duality.
Yeah, exactly.
Yeah. So you can put it into your pocket. You can
on my ears.
not necessarily here.
You can put it somewhere else. Okay, I don't know. Yeah, that's why I have to come early. Is it better like this? Is okay?
Okay, in your
Thank you. Yeah, thank you. Thanks very much. So I won't be able to explain the intricacies and details of this work because it's just complicated, and the core of it, at least to me, seems to be lots of complicated calculations, which of course nobody wants to see. But I'll try to explain the picture and see how far we get. So the first thing is to say, what is this duality? What is this action angle duality? So we have and I'm just going to write it relevant. So it's a simplex.
Yes,
this one?
Better,
This one, the fat one.
Yes, it is much better.
Okay, I'll try. This is the famous MGU chalk that everybody likes.
Yes.
Yeah, okay. But I have had very rare chance.
Symplectic manifold with
A symplectic manifold, yeah. So, and it says, so let's suppose, so this is a statement, this thing about action angle duality is a statement about coordinates, in fact. So let's immediately suppose that we have choice of coordinates on here, and we have, so omega is dp wedge dq, is a standard thing. And suppose that we have a collection. So this is an integrable system. We think of it as specifying a ring of functions. So these are a ring of with n independent elements. So they depend on Q and P, right? And this is a functional dependence on Q and P. This is kind of indicated. And there are n of them.
what's it B? What's P here?
QP very canonical variables. Just canonical variables. So I like in every classical mechanics.
QP or
In classical mechanics.
Okay, sorry.
All the usual conventions of classical mechanics
Okay, okay.
that everybody uses. So omega is symplectic, this is dq dq, and
How many H's?
n, an integral system. So suppose, so I'm just saying, the thing is, ну, у нас есть международные участники, да? Хорошо, okay, because otherwise I could say it very quick. У меня очень много заметки, так, если я все пишу на доске, мы будем очень долго. So the thing is that, yeah, suppose that it's integrable system. Suppose that these are all in involution. Okay, so then in this case, of course, as we all know, there will exist a change of variables, change of local variables to action angle, so-called action angle variables, so that this ring is the same as lambda 1 up to lambda n, and that this is, and that omega is equal to d lambda wedge d theta. So I mean, this we'll always do, and we can always.
H.
This is a family. This is a fancy H, right? This fancy H has. All I'm saying is that it's a ring, right? So H is a subset in C infinity M, which is generated by this.
But what it means? Lambda 1, lambda n.
H1. HK, the cross bracket is 0.
H equals.
So this guy is the same as this. All it says is that if I tell you the lambda 1 up to lambda n, this is the same as telling you this set is the same as H1. It's just a, yeah. So it's a canonical transformation which transforms QP to lambda theta, for which this functionally independent set of n-dimensional functional independent functions is spanned by this functionally independent set of functions. They're just the same. Well, I mean, that's the standard thing. But the point is that what you can also do, I mean, it just kind of, nobody ever, well, nobody would worry about it because it just seems too silly. But we can also consider this family of functions, which is generated by P1 up to Pn. So they will also be in involution. So of course it defines Hamiltonian system. But if I write that Pk is equal to Fk of lambda theta, right? Because it's an invertible transformation. So of course there's an expression of everybody in terms of everybody else. Then what that says is that this is the same as F1 lambda theta, Fn lambda theta. Okay, so this collection of functions is generated by these functions of lambda and theta. And we say that this collection of functions, right, which notice that it's a set of functions, right? So it's not just, of course, everything lives up here, and up here doesn't care about how you write it, but we think about presenting it in terms of some collection of local coordinates, Q and P. So it looks like this collection of functions. This is another collection of functions. Both of them independently define integrable systems, but the action coordinates for this system are the P coordinates of this system, and the action coordinates of this system are the P coordinates of this system. So you can always do that. There's nothing very remarkable. But what is special and which is rare is when these, so this is some concrete thing, right? There's some like half P squared plus V and other gadgets like this. But now these, which they exist in principle, we don't expect them to be nice closed form functions, right? We don't expect to be able to write this down as a function of lambda and theta. It exists in a Platonic sense, but to have some, so I would say that maybe we should call it something, maybe instead of calling action angle, let's call it manifest, right? So you really see it, manifest action angle duality is when these FKs is concrete, can be concretely seen, right? Is concrete, are written in closed form. So my co-author Fehir, by the way, these results, everything I do is obtained together with Fehir. We have several publications on this. And I'm afraid I don't really, you can easily.
You say statement, I didn't understand your statement.
Okay, so this construction is evident, right? But the thing is that in general, what I don't expect is I don't expect to be able to do this and obtain concrete functions which are just in closed form. I expect to get something which usually it's very difficult. I would expect it would, yeah, exactly. And actually, I was thinking about, because I discussed this with Lutzi, because we've actually basically never agree on anything. In fact, our collaborations are very messy. But he likes to say that these should be functions of some reasonable physical type. Okay, but I insist that in general they will not even be something you can write down. And in fact, I tried to produce an example which I would show to you, but it just became too complicated. So I cannot, it's not excluded that you can do it. But for example, if I take the problem of two centers, Euler's problem of two centers, when he invented elliptic coordinates, right?
What's your statement? What's your statement, Ian? What's your statement?
Well, my statement is that if you do this in general for a generic Hamiltonian, for in a generic integrable system, and you do this procedure, you will not succeed to write these f's as some concrete functions of lambda and theta. You will not succeed. But if you succeed to write them as some generic, some concrete functions of lambda and theta, that's already very special. And this is the special thing when I will say that we can call it manifest. Right? Where manifest means concrete. Concrete.
So you mean that if you will find angle action variables, you say it's a good case. And in this case, what you will do?
You will always find action angle variables. There's a theorem of Liouville which says that you will find action angle variables for this.
What's
because
your statement? Yes.
So the point is that when you do this in general, for example, I mean, the problem is so difficult, I didn't even succeed in doing the calculation, so I abandoned it. But if you do it, for example, for the problem of two centers of Euler, which is just 2 degrees of freedom, and try and write down some functions of lambda and theta, which will be, you can really write it down. So some function, so you have your p's here. You want to write down some functions of p1 and p2. You don't care what, so that when you see it in terms of lambda and theta, you can just write down in lambda and theta something like a half lambda squared plus v of theta. I mean, of course, then that would be fantastic, right? That's an extreme case. That's an extreme case. But just any closed form function of just a concrete function of lambda and theta. This is rare.
Yes. Okay. Rare.
And this is the case that I would call this occurrence manifest action angle duality, because it's really manifest. Now, in all of the cases which we look at and which people like, because this is a business which was really, I mean, I would say it started by Reisenhaus, right? So Reisenhaus, he had a big activity in this direction when he was interested in these many body systems. He was interested in systems like Kolozsvár-Moser type and more general versions. And he had a kind of technology for doing it, which was essentially Poisson reduction, which is the thing which I'm going to explain, the thing that Fehe does a lot of that. And the systems that arise, in fact, you do start of systems of many body type here, and you arrive at systems of many body type here. So that is even more remarkable, right? So that is the situation we're interested in. Okay, so when this arises from Hamiltonian reduction, then you actually have something useful in your hands, because this gives you help to be sure of having completeness of flows, because that is an important ingredient in integrability. Not just this, but you'd also like to have completeness of flows. So I'm going to just quickly try now to summarize the reduction picture. I'm not going to go, as I said, maybe an advantage of explaining this such a long time after doing it is that I maybe can appreciate that nobody wants to see the calculations. If I had told you this immediately after doing it, I would have been so distracted, so fascinated by the calculations. Of course, they're too complicated to get into them deeply. But because the disadvantage is that I don't remember it so well. So here's the reduction picture for, I think this is rather clear. So the reduction picture. Let's try and use this die. So Hamiltonian reduction is rather standard, but I want to just make a picture which is perfectly adapted to understanding this duality project. So we suppose that we have a symplectic manifold, or I'll write it like this. And suppose that G acts on there, where G is a Lie group.
G symplectic, it is acting by symplectic.
Yes, I am saying. So it's a symplectic group action generated by some. Now, the thing is, that's what I want to say, is that this should be generated by some, so it's a symplectic action, and it should be generated by some family of functions. So you can think of this as like the momentum map, right? But there are more general versions of this than just the standard momentum map. In particular, there's this Poisson-Lie group situation in which this is what we are talking about. So I'm not going to, I don't want to go into details, but the idea is that you have on here, you have a family of functions. You have a family of functions in C infinity M with the property that if I take an element in here, then for this thing, take the Hamiltonian vector field of this, look at its value at a point in M, and this will be this vector, which of course lives in T, it lives in the tangent, lives in the tangent space to M. This Hamiltonian vector field that generated by this function, which lives in this family, right? I'm explaining the key property of this family is that if you take any function in here, you look at the Hamiltonian vector field, you evaluate it at the point of the manifold. It's of course tangent to the manifold, but it's actually tangent to the group orbit on the manifold, right?
It's tangent to group.
It's tangent to the group orbit, yeah. So this thing here, this xm, if you like, this for all phi in this family, this Hamiltonian vector field at a point M, or even without that, by the way, it's equal to, well, this is a standard notation, but anyway, this for some x in G, right? And in principle, this x, of course, x depends on phi, but it's not a constant. I mean, it's not a constant, it moves around. So if I take M, then this guy will depend on M. And xm, well, xm is the vector field, which is like, sorry, it's a vector field, which at the point M is like the curve e to the tx acting on M. So that gives you a curve in the manifold, which represents this guy, where x is the algebra. So just it's, all of these are different ways of saying the same thing. It's tangent to the group function, right? So I suppose that I have this set of functions. If I have this set of functions, then they just behave like, sorry, I'm so stupid. I forgot to say, I'm sorry. There is one important point which I shouldn't say. There's the key idea, the main idea of Hamiltonian reduction is that I have this thing here which acts on here, and I decide the main idea. It's just one main idea. Very simple. So I should write it down. The main idea is to restrict from, so in principle, we look at all functions on M, but in fact, we want to restrict from all functions of M to invariant functions on M. Yeah. Okay, so that is the plan. That is the slogan.
But don't you need that?
These are not G invariant. These are not G
invariant with respect to GDEq.
Okay, wait a minute. This is technical stuff, right? But this is very simple. Let's understand the very simple thing, because everybody should understand it. It's the main idea. So we have a manifold, a differential manifold. We have a Lie group acting on its smooth action. The main idea is that instead of thinking of all the functions on the manifold, we consider the functions which are G invariant. So I mean, very often in these rooms, there is a bottle sitting right. Sorry?
You restrict yourself to G invariant.
Yes. So imagine that this chalk is spinning in space, and it's all described by, Newton's equations. And of course, every particle in this chalk can be described, and it's all defined by Newton's equations. But if we don't notice how it's spinning, so that we are not interested in any functions which depend on this action of SO2. So we throw away the function not invariant under this SO2 action, unless for some reason we are making a video in which there appears a thing here like I love Julia, and it's written and it's spinning. We want to see, you know. So we throw away, you know, unfortunately, Newton's equations give us too much information, but we throw away the functions which are not G invariant. So we keep only the functions which are G invariant. So on the other hand, all the machinery is defined on M. And on M, we see all functions. And suppose that amongst those functions, there is this collection of functions which has the property that the Hamiltonian vector fields are tangent to group orbits. Then these functions, now, as we put ourselves in this new regime, these functions are just constants. They become for us constants. Before they were not, but they become, when we go from here to here, these functions are constants. So we just fix them, for example, by initial conditions, or whatever you like. And standard machinery for doing this is to use what's called the momentum map. So people have seen this, or they all know about the momentum map. But sometimes if you insist on having something very formal like a momentum map, you give yourself too many conditions to check, and actually this is sufficient. This is not a big deal, by the way. Usually it's not a big deal to get something which is a proper official momentum map, but still it may be convenient not to worry about that. So this is a diagram I wanted to consider. So we have our symplectic manifold here. And we can restrict. Okay, we restrict to a submanifold, which comes from fixing all of these functions. Now you have to fix them in a consistent way, right? Because if f is in here, then f squared is in here and 3f is in there. So you cannot put f equals 13 and 3f equals 4. You have to do it in a consistent way. So level set, yeah. So there is a fancy way of doing this by fixing it. You choose any homomorphism from here to R and fix it to be 0 or something like this. But anyway, or you can take a generating set for this and fix them. But you fix in a consistent way all these functions which have this property. And this will give you a submanifold.
You mean M0 is...
So M0 is fixed. Let's say that this is fixed values of phi in phi, right? So of course you have to fix them, as I said, you have to fix them consistently. So I mean, I can just explain. Well,
you mean all the functions are constant?
Yes, exactly. They are constant. We already agreed that they are constant because of this plan, right? Because of this plan, they are constants. But you can, of course, choose which values of the constants you fix. And when you choose different values of the constants, you'll get different. M0. Level set, yeah. So for example, I can say that this is equal to, this is generated by all phi alpha for some alpha in A, right? So suppose that this exists. So, and this is equal, so this is such that, and phi alpha in A, this is a generating set. So this is equal to, I don't know, f hat. And this has the property that if I take phi alpha, if I take phi alpha for alpha in B, for B strictly smaller than A, then this is definitely smaller than F. So it is the smallest generating set I can put in there. And then after I do that, then I fix phi alpha. So M0 is going to be the intersection of alpha in A of phi alpha of 0, say, phi inverse of 0. because I can always add any constant, it doesn't change the fact, right? These are defined by the property of Hamiltonian vector field property. So of course I can add a constant to these phi alpha, it doesn't change anything. Нет? It's очевидно. Вот это, I mean, if I take phi alpha plus k, this is equal to, it doesn't change, this is just adding a constant. Right, so I don't change anything. So I without loss of generality, I can assume that these are such that I take the inverse integer of 0. Anyway, this is, as I said, it's rather standard stuff. You can think of this as like in the momentum map situation. But then from here, I have to project to the reduced phase space, the reduced space. So this is the reduced space. And the reduced space is M0, right, what you were here, factored by, restricting from C infinity M to C infinity M to G invariant functions. It means projecting from M to M mod G. So it's associated with projection from M to M mod G. There are all kinds of technical requirements that you have to fulfill to be sure that everything is safe and as it should be. But let's assume that everything is regular in a nice way. So
essentially, I'm reading the space of orbits.
Yes, but I have to factor by the residual symmetry. So let's say some residual symmetry. So this is a subgroup in G, because you are interested in the G invariant functions restricted to here. But when you are in some submanifold, sometimes the group action will take you away from that submanifold. So you're not interested in those, you just won't see them. You're just only interested in the elements of the group which stay inside this submanifold M0. So that is the reduced phase space. And all of this is, is existing in the world of differentiable manifolds. None of these people care about us with our stupid local coordinates, right? They are living an independent life. But we come along and we put local coordinates everywhere. So we will put local coordinates here, and with respect to these local coordinates, we can choose, as you will see in an examples that I show you, two different choices of local coordinates, which is, there will be local coordinates on here. So let me just think which it goes in this way. So I've got a choice of local coordinates on here, which are represented by this representation of the projection, to what I can call M. So this is a calligraphic M. This is a calligraphic M0. This is an ordinary M, and this is an ordinary M. And then I've also got this one.
What is the difference between left, going to left, and going to right? What's the difference between left?
Well, as I'm saying, we will see in examples which should make it clear. Okay. So the thing is that, I mean, there are many, many ways of choosing local coordinates on here, right? But we will see two privileged ways which are adapting. They are generated by the whole constructions, right? Everything depends on the choice of the initial manifold, the choice of the group action, the choice, as you will see, of Hamiltonians up here, which we begin the procedure with, right? But when you do this, you naturally end up wanting to choose local coordinates in two different ways, as you will see. And when you do that, you end up with these two. This M is like a space of local coordinates. It's a copy of R2K, and this is also a copy of R2K. And from here, let's just say that we map from there to Rn, and these are the
local chap.
Yeah. From here, you'll have these action variables. So this corresponds to the map from to the H's, and this corresponds to the map of the P's, which were in duality. And the dual version of this picture, which is
this set phi alpha generate F in the sense of linear algebra or as a ring.
You are
which you
right,
just
by the way. That's a
just
good point.
erased
Yes.
just now.
All right. So let's suppose that here it's 2m. So it's something else. It's bigger. Did somebody? Is one of the people say ask something?
Sorry, this set phi alpha generates f as a ring or as a linear space.
As a ring. Yeah. Yeah. As a ring. Yeah.
Okay. Thank you.
Yeah, because of course I'm going to say, so yeah, as I said, I mean, if phi alpha, if phi is in F, then of course phi squared was also in F. Of course, right? Because if I take the Hamiltonian vector field of phi squared, this is equal to 2 phi. So of course, if this one is tangent, this one is also tangent. And as I said, I cannot fix phi to be 1 and fix phi squared to be 13. I cannot do that. I have to do it consistently. All right. I know it's obvious, but I'm trying to.
What you can do.
So I want to draw the dual picture of this, right? Because it helps us understand what's going on. All right. The dual picture. Well, I'm gonna when I draw it, it's also obvious. Everybody knows. Let me just draw it, and you'll see what I mean. So, if you look at the functions which are defined everywhere, so I've got the arrows go in a different direction. Right, so I'm going to pull back the functions. So what I have started, in a way, I'm going to draw it like backwards. But as I said, the whole thing is generated by the choice of various things. So the first thing is the choice of the starting manifold, but there's also the choice of the functions up here. And you will see the examples is what I want to show you. So you have two families of functions defined here. And I'm going to write them here. So you have I star of H1, okay, and right, so those are two families. This is a family of commuting functions up here. As you'll see, they are always just trivially, they are like absolutely bisplatner here. And this is a different function of commuting function, different family of commuting functions here. Like, for example, functions of P, right? If you take functions of P, then of course they all commute. There's nothing to do. They are not even interesting. But you always start off with something like this. This is all the functions of P, and this is all the functions of Q, something like this. So you start off with these here, and they come from pulling back from here. So they sit up here, but these should now be, on the one hand, pulled back from some functions down here, also pulled back from something here. And as I say, H1 and H2, they live here, so they don't care about local coordinates. H1 and H2, they do not care about local coordinates. This guy also doesn't care about local coordinates. So this corresponds to some functions here, right? So they correspond to, this is just this set of functions, but thought of down here. Because what are the functions on this space? The functions on this space are just the same as the functions on M0, which are G invariant. And they are the functions on here restricted to this guy.
No,
No?
This some direction leaves in C infinity of M to M. Yeah.
Yes, and also therefore by restriction to M0. Yeah.
Yep. And
yeah.
No arrow goes from this M calligraphic.
From here, no, no, from here, but I'm going to write it.
Yeah, but you see,
no.
We took. Sorry. These guys are from here, yes.
Yeah, but they're restricted to M0. I just didn't draw I didn't draw this one here. Of course, they come. There are here as well. I mean.
Yes, but.
So there is an I star here.
Yes. Correct, but.
Basically, just the same thing.
How do you know that something from here corresponds to?
Well, let me finish the diagram. So first of all, as I say, there are functions down here for which these are the pullback. That's just how this is just a tautology. Because what is a function here? It is a function which is defined on this space, but the functions, all the functions here are just the invariant functions on M0. So they are the ones, they were already invariant, right? These guys are already invariant. Ah, by the way, no, but they are. Sorry. If I tell you that they are pullbacks from here, then they must be invariant. Right. So that's the thing which I didn't underline. So H1 and H2, they are functions which commute separately, but they are also invariant.
Yes.
They are also invariant. I didn't emphasize that. Because they are invariant, they can certainly be written as pullbacks from something here by tautologically. Okay. On the other hand, everything here, I mean, this is just an isomorphism, right? This is just these are just choices of local coordinates on this differential manifold. So of course they can be written, these functions are some local coordinates of some functions from here, and from here these will be two families, right? And one of them I'm going to call p hat in these choice of local coordinates, and the other one I'm going to call h hat. And here I've got H and P. So these two, this one represents that, this one represents that, and this one represents that, and this one represents that, but just in different coordinates. And you've got a map. You've got, because all of these ones here are all isomorphisms. So if you just combine them, you get a map from here to here, which is the change of variables mentioned already. It is this change of variables, right? It's just this R is this change of variables. And in this case, well, it just goes in the other direction. And this picture is a kind of universal picture, and it's what is used to construct examples of systems in action angle duality. Now, the only chance, in my opinion, of a system which we are able to just all write down on the board and understand in 10 minutes is the baby version of this, which also doesn't look very, very exciting, but it's sufficiently, important example. Everybody knows. Usually this is a point where people should sit back and feel comfortable because they say, yes, of course, we've seen this before. Right? Just to describe the Calogero-Moser system, decorate it with this picture, right? So there will be nothing very exciting, but if I write this down, it will allow me to refer to it to tell you some much more complicated things where we will probably start to get lost. Okay, but at least we have something to refer to. So I can fix it. So here is an example of what I'm talking about. So the example is Calogero-Moser. So we start off with M is UN times UN and omega of omega at the point xy. So I should say omega at the point xy is equal to trace dy wedge dx. So this is absolutely just dq wedge, dp wedge dq. It's just dp wedge dq where I take dyij wedge dxji. They're canonical. They're just n squared of them, right?
Some of them are P, some of them are Q.
I'm just saying this is P and this is Q. This is just this is n this is 2n squared dimensional real manifold, right? But it's just a convenient way to write it because now I want to say that there is a group on here. So the group is UN. Okay. And the group acts on here. So G acts on M. I won't write all the details, but G. So let's say that G dot XY is equal to GXG. This means inverse. Right? This I know this is a notation which is, well, you are all international. So that's an action.
Because this unit are group, you write it this way.
Yeah.
Okay.
I have discovered living in Russia for many years that this notation is not popular in Russia, but I think everybody knows it. It's just, I know very often I write to people say, well, no, it's dagger, but I think,
Not here.
you've seen it many times, right? It's normal. But the point is, before I came to Moscow, everybody used to write. In the UK, everyone writes it like this, but it means complex conjugate transpose. So, yeah, by the way, it's in Russia, it's popular to write it with a star, right? Correct? Yeah. Okay. Sorry, excuse me, but anyway, why not write it with a star? Okay. Yeah, because I was used. There are different traditions in the UK, so I should adapt, of course. So now, well, okay, this F, which I mentioned, it happens that it's generated by this map. So I fix J of XY is the commutator. Right, by the way, this action is easy to understand why it's a symplectic action, because it just obviously preserves this. It will not change anything. If I put a G everywhere, they will cancel. So it's easy to see this is a symplectic action. And this map, right, which is obviously is a map from this space here to the Lie algebra. Sorry. I'm so sorry. Of course, I'm so sorry. I'm so sorry. I wrote it down wrong here, actually. That's really stupid. Okay, so this lives in the Lie algebra of G. And the point is that F is generated by functions of this form. Well, this is the Lie algebra of SUN. Okay. And so, right?
Just so we take X and Y, take commutator, yes, and consider oxide at the point corresponding to
Mm-hmm. Well, it's easy to check. Easy to check that. What should I do? I should put that with, if I put X of let's say phi of C, if this is phi C of the point XY is equal to CX CY, right? It's easy to check that this has the property. And this is just the infinitesimal version of this. The commutator.
yes, of course.
If I take this as phi C, that's easy to check, i.e., if I take omega of C, this is equal to d phi C. That's an easy exercise. We could do it, but I think the point is, everybody can check it. It's easy to check. That is what is meant when I say that this generated. This illustrates what I meant about the generating. This family of functions generates the actions, so they can all. If I decide to fix to M to G invariant functions on here, these are just constants, so I can fix the value of this commutator. And so we fix this to be, so this is supposed to be an element of the Lie algebra. So let's fix. So first of all, choose arbitrarily some element with a hat on it. I put a hat on it because later I will remember. It should just be some element in Cn. Some vector, any vector in Cn with length squared equals n. Okay, and then I choose this to be I times identity matrix minus V hat V dagger. Right, so that is this step. Right, so I start off with all xy in un. This started off being un times un, and I restrict to pairs x and y satisfying this. Right. So I impose this condition, and that defines the submanifold. Then, well, how to go from here to here? I should look at the, I should factor by the isotropy subgroup, but actually there is a more convenient way to do this. So let's just suppose that we're looking at this and we change, let's write xy, right? So you take any xy is anything in here, and I can always write it as G, let's put G dagger for convenience, acting, right, according to this rule here, on x hat, y hat, with, and here are two natural choices with one, x dagger diagonal, 2, y dagger diagonal. Okay. And these will correspond to these two choices of coordinates. Yeah, they will do. We haven't got there yet, but they will do. All right. So now, I mean, you can always do that. It's just a question of choice of basis, right? You're going to choose a basis so that x is diagonal, or choose a different basis so that y is diagonal. So this thing here, which lives in the Lie algebra, you decide to choose a basis, so it's like that. On the other hand, this v hat is fixed. It sits there, and it's the way it's written depends on the basis that you've chosen. You've changed your basis, and it will look different. But now you've fixed your basis so that x hat is diagonal, or you choose a different basis so that y hat is diagonal. And now, what you're looking at, again, I want to just keep these because it's nice to be able to refer to them. Let's just look at we'll do a little calculation here. So it's a pity I can't fit it all on that small board. Probably could have done if I'd been a bit more careful. So I've got G dagger x hat commutator y hat G equals IE minus V hat dagger. And now I can just put G across. Okay. So of course the E will stay the same. But now this will get acted on by G. So I can say that this is the same as this, and I'll just remove the hat. So now what have I got? I've got that V is G V dagger, V hat, sorry. And now I'm in the situation where either X is diagonal or Y is diagonal. And I guess everyone can appreciate that it's a totally symmetric problem. I mean, the exercise I'm doing does not depend which one I choose. It will just be precisely the same exercise. So let's just suppose that I'm pretending that X is diagonal here, right? So suppose X is diagonal. Let's call it Q1 up to Qn, because they will be the Q coordinates of the dynamical system we're looking for. Now, in this representation here, where I had that X was equal to G dagger X hat G, clearly X is diagonal. This is not going to depend on what happens if I change G to TG, right? If T is diagonal. So I have this freedom in adding this T. In this G is defined up to the G which does this, which diagonalizes X. It's got some freedom. I've got this T in here, and this T can be used here right? T is an element of U1 to the n. So this one can be used to rotate each one of these elements V so that without loss of generality, in other words, using this freedom here, I can say that Vk is in R positive, right? It can all be this extra U1 freedom can be used to rotate them there. And so I can just say that these are real and this is transposed. So the only time when I can find solutions of this is when I keep those G's for which so I'm insisting that X hat is diagonal, and now I'm only going to keep those G's for which this is a reasonable relation. Otherwise, there just won't be any, and you just throw them away. But you go to a different one, and you keep every time you find one, you put it in your bag, your M. So now when you look at the diagonal part of this, of this relation, so the diagonal part of this is 0 because X is diagonal. So diagonal part of 0 tells me that the diagonal part of this must be 0. But the diagonal part of this tells me that 0 is I times 1. So this is E. So this is 1 minus mod Vk squared. For all V, well, Vk squared without a mod because they're just real, they're just positive Vk squared. So therefore, you see that i.e. Vk equals 1 for all k. And now for k different to L, we've got I qk minus ql y hat kl is equal to, so we're on the off diagonal part, so the off diagonal part of this is 0, and I've just got minus I times 1, because they're all 1. So it's just VKVL, which is 1 times 1. So it's that, and I get that YKL for k difference L is equal to minus 1 over QK minus QL. So I've got my X, and I've got my Y off diagonal, which is a function of Q's, and so the diagonal part of Y is something, and so I can write down the solution of this. All of this is, I guess, clear enough. So I can, as I don't have any space, I'll just remove this. And I'll say that, by the way, I need to keep this. So there are some calculations, and the result is that X is like that, and Y hat KL is either equal to something when it's diagonal, let's call it PK, or when it's not diagonal, then it's that. Okay, so that's the analog. Sorry, that's not the analog. That's what happens here when I pass to here, and of course this one corresponds to the choice number 2 when Y hat is diagonal, right? And of course you're getting them. Now what are the, so I mentioned that there is this dual picture, and I mentioned that there are these functions in here. So what are the functions which I like, right? The functions that I like, which are appropriate here, are, let's say, I'll need to make it a bit smaller. So fix the functions. So H1 is equal to the set of H1 and H2 is F1 and so on. And what is HK is equal to 1 over K trace ix to the k, well, let's say iy to the k, and fk is 1 over k trace ix to the k, right? They are perfectly good functions on here, and it's completely trivial to see that they commute, because indeed this is just functions of q, and this is just functions of p, right? Well, in the sense that this is q and this is p. So of course all the q's commute with each other and all the p's commute with each other. So this starts off. On the other hand, what you're seeing is that so these two functions here, they are just this collection. Traces of powers of x and traces of powers of y. And when you look at what they are, they correspond to traces of powers of y and traces of powers of x. Well, the traces of powers of y are given by the traces of powers of this, which I guess people know is the usual lax matrix for the Colorado-Moser. All right, this is just IP1, IPN, and here the general term is -1 over QK minus QL. And then here it's the to be skew symmetric. This is the standard lax matrix for the Colorado-Moser that everybody's seen. And traces of powers of this give you the standard commuting Hamiltonians for Colorado-Moser. So this is your H here. And the P's are the traces of powers of x squared. And the traces of powers of x squared will just give you functions of q, which is, of course, not interesting. On the other hand, when you look at the ones over here, these traces of powers of y squared, if you had chosen the alternative where y hat was diagonal, then you would just have done exactly the same calculation. Everything would be symmetrical. Then you, so in this case, the dual system is just the same as the one you started with, right? In this case, and this map is the diagonalization map. So the map is, you start off with this lax matrix, right? So this is the lax matrix, and you say, well, L is equal to G, I don't know, something. Let's call it lambda. Okay, so there exists a G which diagonalizes. Of course, it's some horrible function of Q and P, but there exists choice because every matrix. This is a unit. This is in little un. It can be diagonalized using a unitary matrix, and this depends on some complicated group valued function of Q and P. But the result will be diagonal, and this is precisely what this R is, right? That this G, the G which does that, encodes R, because you apply the same G to this guy, and then you'll say that L hat, once you find G which diagonalizes, is just exactly this one, G dagger X, because it's the other way around, G. So the guy that diagonalizes this is applied to the X to get, and this defines your R, this map R, in this case. Very good. So that is a picture that's not so difficult, but now I'm going to show you what sort of results.
So this example is finished,
yeah?
Question, why UN? Why not another person simple?
Yeah, well, it can be done much more generally. It can be done more
You
generally.
said that you will consider example.
This is, we just finished the example, yeah. Huh?
I saw no specifics of UN.
No, it's true.
Where does it?
Well, just because I was, I could have done U2. It would, maybe U2 is too small, but no, I tried to keep it as concrete as possible. I think it's okay for SL as well. Yeah, I think it is, and people like it. Some people like to do it with SL. Yeah, it's okay.
Okay.
But just It's not a very big deal. Okay, so now what I want to show you now is this result that I have with Lotzi, and try to make comparisons with that. So we can't afford to keep this if we're going to keep this and refer to this. Although I think everybody can remember it. Let's just say it's Kolodro-Moser. Let's stage Kolodro-Moser. M is UN times UN. G is UN. J XY is XY. And this is equal to IE minus V dagger. And I think that's probably enough. Omega equals trace dy wedge dx. That's probably enough. That's just encodes everything that we had. Just to remember. So now this thing. So in this case, the starting manifold is SL2NC. So you think of this as a real manifold, and it's the fact that it's a group is only used in order to say the following thing. This is used is to say that it can be factored. And this factorization, when I write this, this is SU2N, and this is upper triangular with real positive diagonal. B, yeah. So actually it's S, I should say S. It's if I start with SL. So this is upper, I'll write it in a minute. But the point is, all I want to do is to just notice just that this is something very, very familiar to all of us. This is just Gram-Schmidt. Right? There's nothing more exotic than Gram-Schmidt here. We all know that if I give you a collection of independent vectors, you can always, orthogonalize them, and you can do it one step at a time, and that's where the upper triangular appears from. All right, so K is equal to SU2N, and B is the set of upper triangular real positive diagonal. But the thing is that, okay, let's just write. So we also have K is the Lie algebra of K, and B is the Lie algebra of B. And we have that R.
Direct product is of groups or of spaces. Do they commute?
Well, as I said, I mean by this I mean Gram-Schmidt. What do you mean? Do they commute?
Well, if you take direct product of two groups, you assume.
Yeah, but as I said, I don't think of this as a group. I mean, I only say that it's a group. It's a real manifold, and everything in here we use Gram-Schmidt to write it like this. You know, so well, it will be mentioned that it's a group sometimes for convenience of calculation, but it's not crucial here. The important thing is that it's a differential manifold on which K acts. We're interested in using because K is the group on which acts in here. They are relevant. So in this case, I should probably try not to put in too many technical parts because people have seen it before, or it's not possible to catch it in 10 minutes. So on the other hand, probably I don't need that either. The Lie algebras are just kind of obviously denoted by the same letters. So this is Gram-Schmidt. Let's just say, oh gosh, somebody there. Okay, so this is Gram-Schmidt. That's all I mean. And what it means is, so let's just say that the K actions. There are two natural actions of K on here, right? So one is I take an H in K, and I make it act on G. So an element in here is denoted by G. And let's put a little L under here to say, I mean, the one generator. So this is just HG, right? So H is in K and G is in here. But the other one is with an R, which is GH inverse. Okay, these are just two actions. They commute these two actions. And they have momentum maps. Now, the point is that there is a very nice way to put a symplectic structure on here, generated by this Gram-Schmidt thing, uses this R matrix technology, and we can write some formulas. It will fill the boards and everybody will get lost. But there is a Poisson bracket, which is reasonable to define on here. And I'm sure you've seen it before as well. So I would just, instead of filling the time with that, where I think we will all get frustrated, I'll just say, to some extent, people have seen that, and there exists a natural Poisson bracket on here, which respects all of the things which we are seeing. This will become a Poisson action and so on. But what I want to be clear about is that the momentum maps for these two things. So what are the momentum maps? Momentum maps. So this is this space F. Right? So these are the guys which generate the action. So if I write G, let's take G is this, I'm calling it M or G, so it's this group here, this SL2, and I take an element in here, I can write it, on the one hand, I can write it as something in K multiplied by something in B. Or I can write it as something in B multiplied by something in K. There are two possible different ways of writing it. And the momentum maps are one of them is to take G, right? So this G, it lives in M. So this G is the analog of the pair XY. So I just tell you, the analog of the commutator XY is to extract the left. Okay, so that is the momentum map which generates this action. Okay, you cannot understand why it's true because I didn't give you all the formulae, but it happens to be true, right? Without all the details. So there is a Poisson structure on here. When you turn the handle, you do something analogous to the thing which we did here, and you will see that indeed any function of BL is tangent to this action. And on the other hand, the other momentum map is that G is mapped to BR. Okay, so the analog of this, we fix the values of the momentum map, means fixing BL and, So we have these two actions, and using these two actions, so let's say HLG equals HG and HRG equals GH dagger, right? So we have these two actions, and we use these two actions to build this this symmetry group. So the analog of this G here is what I'm going to call K plus times K plus. All right. In other words, K plus. So what is K plus? So K plus is S, because I'm in here, it's S of UN times UN. In other words, an element in here is the set of all matrices with 0, 0. And this is in UN and this is in UN and the determinant is 1. It just means special. It just means the determinant is 1. So I'm taking something in UN and something in UN, but I'm requiring the determinant is 1 because I'm supposed to live in there, right? Because K is SUN. Yeah, block diagonal, and each block is unitary. And so now what I'm going to do is I'm going to take the action on the left with K plus and the action on the right with K plus. This is my symmetry group. This is the analog of this UN here. So I'm interested in functions which are invariant with respect to the left action of K plus and the right action of K plus. That's my plan. That's what I want to do. And so that means that we don't fix BL and BR, but we fix the parts, we fix the parts of BL and BR which are relevant to here. So we factor by this normal subgroup in. So this is a normal subgroup inside B. That's easy to check. But it happens that it is a normal subgroup and we factor by it. So we're going to fix BR to be something, right? So it's going to be, I don't know, alpha, beta. And then here we don't care, right? And I'm going to fix BL to be something. All right, so it is the choice of gamma and delta and alpha and beta is the analog of this. It's a momentum map constraint because it represents these actions. There are choices which we are allowed to make correspond to actions once we decide that we're looking at invariant functions which are invariant with respect to this group. So I should do that. And now there is a funny result, which is just, we can just see. So let's have a look. I'm just going to show you this because it's quite funny. So actually, let me just say what the choices are. So the choices are, so the choices are BL and BR. And so let's fix BR to be X inverse, and here's just something. Okay, and X is, let's say X EN and EN. Okay, so X is in R plus, because it has to be in plus, otherwise it wouldn't be in B. And we fix, and BL is fixed to be, probably it's like this, Y inverse sigma. I won't tell you what sigma is in a minute. And then it's just something, because remember, I don't care what this is. And here I've got to put Y. And now Y is in R plus. And sigma, well, I didn't tell you what sigma is, but there is a sigma which we're going to tell you in a minute, right? But there is a very special sigma which we want to fix. And that's the momentum map construction. That is the thing which we want to fix. Now, I'll tell you what sigma is. Sigma is the Poisson-Lie analog of this. This, by the way, this construction it's probably variously due to Alshanetsky and Perelomov, Kazhdan, Kostan, Sternberg. It's variously due to different people, but this constraint is typically known as the Kazhdan, Kostan, Sternberg constraint, and this sigma is the group analog of this, which means that actually it's just the exponential of this. And the exponential of this happens to have just the same form. This is a rank 1 deformation of the identity, right? It's just you take the identity and you add a rank 1 matrix to it. And if you take the exponential of a rank 1 deformation of the identity, you get a rank 1 deformation of the identity, in fact. So in fact, sigma is an upper triangular matrix with the property that sigma dagger is equal to, well, we like also to have lots of parameters around, which I didn't put them in here. I could have put a parameter in here. I could have put a parameter and then I would have got something more, but we like when we got more parameters. So this has the property that it's equal to the identity plus alpha v. And this v is kind of the same rule as the other one. So the v, this sigma is a diagonal matrix, is an upper triangular matrix with the property that when you do this to it, you get this. And actually, this is not, don't forget that as before, v hat is just anything you like. So you could choose v hat to be the matrix, to be the vector with just one here. And when you do that, you see that this thing here, the result is a diagonal matrix. And a diagonal matrix is easy to factorize, right, into an upper triangular and a lower triangular. So it's not, there's nothing very technical here. It's just if you choose the right basis, it will be easy. But that's what your sigma is. And those are the momentum map constraints. Now, the next step is to do the analog of this thing which I call case 1 and case 2. So the analog of case 1 was to choose x hat to be diagonal. And case 2 was to choose y hat to be diagonal. And this is where, in this situation, things become much more complicated. So probably I need to have space here, so I'll have to write small. So I've got BR is x inverse, and let's call it omega. So omega is just something. And BL is this Kasdan-Kosten-Sternberg guy, and this new is whatever it is, y. Okay, and now let's suppose that the objective is to have everything defined in terms of KL and BR. So let's suppose that we plan to do everything in terms of K and B. So these are the analog of X and Y. So in X, before we had X and Y, they both are the same. Now they're rather different. X is a unitary matrix and Y is an triangular. And the first thing which makes this tractable is, so first of all, I can choose, I can write for any big unitary matrix like this, I can always write it like this, rho, tau, and then here I can write gamma, sigma, sigma minus gamma, and then some other, right? So this is an element in K plus. This is another element in K plus, and these guys, this is cos theta on the diagonal, sine theta on the diagonal. So this is like a block diagonal element. It's not the most obvious choice. The obvious choice would be to choose cos theta minus sine theta, cos theta, but it just happens to be nicer like this if you do it differently. But you can always write any, this is essentially you've diagonalized it. Okay. You choose to do it like this. Of course, you could make it, you can't make it diagonal because you don't have the freedom of the whole of K, but you can make it diagonal in this blockwise sense by using this thing here. And now, because you are going to forget about, you have the freedom to factor by this K plus action, then in fact, what you can do is that this guy will come through here because this is just, well, in fact, X and X, this is just a character. So it comes through here and you can throw away most of this. You can throw away T by just factoring by K plus, and you can throw away F and H. So I can assume that K has this form. And then I have to keep omega general, right? So I will keep, so now I take B is BR, and then fixing this condition. There are lots of calculations which have to be done. It's complicated and messy, but at the end of the day, the result is you find all the analogs of everything which was done here can be carried out, and you end up with here, and your I have to tell you what the Hamiltonians are that you start with. Okay, so the Hamiltonians that you start with are, so Hamiltonians are, let's define, omega is BB dagger. By the way, it may be B dagger B. It probably doesn't matter very much. BB dagger, and L is K. Okay, I'll tell you what this is. I'm sorry, this is not. So I'm in here. So I also introduce this matrix I, which is En and minus En. It's traditionally called INN. So it has the property that this K plus goes through there. And if I do that, then the two families of Hamiltonians are basically traces of powers of omega to the K, and H2 is traces of powers of L to the K. So you can see that they're invariant. It's easy to see that they're invariant. And it happens that they commute. That's also not very difficult, especially this one. In fact, this result that I'm showing you here does not really involve L. It just involves this. So you end up down here. We started off with this family of Hamiltonians, traces of powers of omega and traces of powers of L. And you come down to here and you find your integrable system here involving traces of powers of omega squared, because you do all your calculations which give rise to this omega. Right. Now, the other choice is, instead of choosing the K to be diagonal, it's diagonalization. You want this guy to be diagonal. So the other choice is to use the freedom in this. To use the freedom here. So I say that this is rho tau x beta. Let's say that the beta is diagonal x inverse, and then here I'm going to put FH. So I can use that freedom here so that beta is diagonal. So beta it starts off as just being any n by n complex matrix. So it's huge, right? I mean, it has what, 2n squared. And you can use the freedom to factorize by these guys to assume that beta is diagonal and real and positive. And that's the analog of choosing y hat to be diagonal. And that involves different kinds of set of calculations. And so I'm going to write to show you what that involves. So if I take, let me see, I just thought of showing you some things. So if I say that G is equal to KB, and that tells me that G is equal to B dagger B. Okay, and suppose I have, so let's just write, I mean, I want to express this condition here in a nice closed form involving only G. That's my ambition. Because I don't want, I can say that that's what B is, but I want to write it as a condition involving G. So suppose that B is equal to, I don't know, alpha, beta, 0, gamma. Right, so these are upper triangular and the beta is just anything. Then beta B. What is beta B? Beta B is alpha dagger alpha. Okay, so alpha dagger alpha, alpha dagger gamma, gamma dagger alpha. And here I've got beta dagger beta plus gamma dagger gamma. Now, if I consider this, beta gamma B minus beta gamma B x This exact has nothing to do with this one. It's just a square matrix, a Hermitian matrix. B dagger B. Right, you add it all up, do all the calculation, and you can see that this can be written in the following very nice form. So this is alpha dagger E minus alpha X alpha dagger alpha dagger alpha dagger alpha, yeah. And here I've got gamma dagger times this same bracket alpha, and here I've got alpha dagger times the same bracket gamma, and here I've got beta dagger beta plus gamma dagger times the same bracket gamma. So if I insist, if I impose the condition that this is equal to 0, 0, 0, y, that is the same as saying that this is 0 and the others are all 0. And it's the same, this one is already 0, and it's the same as saying that this is y. So that's just to show you that I can arrive at this condition. So I can start off with, I can say G dagger G minus G dagger G. What did I have? X 0, 0, 0. By the way, sorry, X should be alpha dagger alpha minus 1 equals 0, 0, 0 beta dagger beta, right? That condition there on G implies that B equals alpha something beta. So I've got a condition on B, which I can write in terms of G. That's the point. And this is actually the formula, which is direct analog of this. And this is a formula that can be massaged and written in. So if you just write it down, wait a minute. Well, sorry, there's another formula. The analog, I've written as something else. So there is another formula which I need to write. So the other formula is that tells me that, and the other formula is that I want to write G dagger minus G dagger, and then I should write something here, and G dagger equals something here like this. Okay. So that and this, by the way, is this should be equal to sigma dagger, and this should probably be y squared, y minus 2. Yeah, right. So this formula represents this formula will represent that condition, and this formula here will represent this condition. And now if I write G equals KB, so that gives me K B dagger K dagger minus and all the others. Of course, you can see that this thing here can be written in terms of the identity minus this guy. And this can also be written because sigma dagger involves sigma dagger involves the identity matrix plus alpha V dagger, right? So that can be also, this E can also be written as something involving the big diagonal matrix plus this. And the result in all of this is you end up, for this condition can be rewritten as 2 this thing, where this was BB dagger. Remember BB dagger, and L was equal to K dagger I minus, well, I should have written it down somewhere. Right. Minus Y inverse omega squared, because that corresponds to the bit when this is the identity, plus Y minus 2 omega. Here I've got L I omega well, probably the best thing is just to remove all of that, because the idea is that there is this technique which you can use to extract the diagonal parts of this, and you end up with this nice formula. You end up with this nice formula: 2 omega minus Y minus 2 omega squared plus Y minus 2 omega L I omega equals gamma, which is involved in this sigma, plus gamma Li plus 2 alpha. Alpha is just a number. And now this guy is W hat. So what's W? W is, because look, obviously, if I just write V like that, this is equal to V okay, this is just W. So this guy is W. So W is a long vector, half of which is just 0. And now once you've decided that your omega, right, omega is B dagger, and B is this. Now you can choose omega to be this diagonal matrix, which this is the, as I've said already 5 times, this is the analog of fixing Y hat to be diagonal, because you had the freedom in the use of K plus to do that. So if you fix this to be diagonal and you write down this, you see that this is actually a very simple to diagonalize matrix. This guy here, it has, I don't know, it's diagonal form. This will be diagonal, this will be something else. Everything is real. Everything is diagonal. Everything you see is diagonal. So the problem of diagonalizing it reduces to lots of 2x2 problems. It reduces to many 2x2, and everybody can diagonalize a 2x2 matrix, 2x2 symmetric real matrix, right? Using an element in U2. So there are many copies of that, and you diagonalize it, and you end up, after you've diagonalized it, you say that this is 2 lambda, where this is the diagonal version of that, minus Y minus 2 lambda squared plus Y minus 2 lambda Li lambda plus minus gamma minus lambda. Okay, so this has to be now because you've got your, so this one here is now not the same as it was there. It's because there's a diagonal guy gone in here and he gets brought into that, right? You understand? It's just you just different choice of. So the same thing will come in here, and you've got plus so minus gamma Li equals 2 alpha, and now this thing which diagonalized lambda, you make it hit here, and you call the answer W. And again, you'll have the same freedom that you can use in this, because you're talking about diagonalization. You've got freedom of adding a diagonal matrix just exactly as you could before, and you can assume that it's real and positive. To be honest, I'm a little bit uncertain about that detail. It seemed to me that you could, maybe there was some problem with that, so I'll leave it like that. In this particular case, I think there's some small that you can't 100% do that, but certainly this one is now is diagonal now. And the thing is that now you can bring this to some form where you can write this formula here is the analog of x commutator y is this when x is diagonal. And in other words, you can write down this, because what does it look like? It looks like, let's see what it looks like. It says, if I take here y minus 2 lambda Li, this is something I don't know, right? This is the analog of y. Lambda minus gamma Li equals minus 2 lambda plus y minus 2 lambda squared plus gamma plus 2 alpha W dagger. And now if I just look at the KL component of this, right, this is a 2n times 2n matrix. So look at the KL component of this. Well, you've got a lambda k, lambda L, multiplying this KL component of this, minus the KL component of this, and so on. So you can just write down the KL component of this is the KL component of this divided by y minus 2 lambda k lambda L minus gamma. And you've got an explicit formula for that, which is exactly the analog of the formula which told you what y was, this formula that y was equal to minus 1 over qk minus ql. So after that, there's lots and lots more calculations that you have to do. But the result of this is you find a different set of coordinates. In other words, you've done these ones, and the Hamiltonians that you want to use are exactly the traces of powers of L instead of traces of powers of omega. And you see that the map between them arose from diagonalizing omega. So on the one hand, you had your, in fact, this is the Lax matrix of the systems which live here. The Lax matrix for these systems is BB dagger, and the Lax matrix for the other ones is this. And they're related just by diagonalization procedure. So you end up with just the example, and I mean, I can write down these huge crocodiles formulas for the Hamiltonians, but they are some formulas, and they have Reisenhaus type. They are the so-called Reisenhaus type. That means that they have the form.
Can we say that today we heard, I want to fix something in my head?
Yeah, something to go home with.
That Ian explained me that what you explained. I just want to fix something.
Didn't you actually?
No. Is it okay to
well,
say that?
All right. Look, what I hope that I explained is I explained that these nice pictures.
Yes.
I hope I explained these nice pictures with two examples, one which was understandable and the other which you can understand. was probably not understandable. I hope some parts of it were understandable.
Well, the first
So-
example is rather transparent. And the second one.
Yeah, the second one was, well, of course, not transparent, because you would need, it would be take me all week to tell you all the details, and you would get completely depressed.
Does the system have any name
Well,
similar to culture?
I'm afraid it probably doesn't. It's probably the BCN case of the trigonometric Reisenauer's system. So actually, the history of this. The history of this is that there is a result. I guess it's due to Inozemtsev and Meshcheryakov in the 80s or something like that, is to how to find a lax representation for, I mean, they did much more. They found elliptic sons and so on, but they found a lax representation of a BCN case. This is something that Olshanetsky and Perelomov had not succeeded to do, not either with reduction or anything. And my friend Lotzi produced a Hamiltonian reduction version of this result in about 2001. And he told me that, in fact, he discussed it with Olshanetsky, and he was hesitating because he said, I don't know if this is interesting. I mean, the system is not new, but, you know, should I do it? And Olshanetsky encouraged him, maybe just being polite. But anyway, he found this Hamiltonian reduction version. And the way to do it is you should start with T star G, with G equals SU of 2, by the way, SU NN. So it's not exactly this system. It's NN, right? NN is the group which leaves this structure invariant, right? Instead of, right? I mean, you know what is NN, right? And you should take the cotangent bundle of this. And again, you should take the action of the same group, K plus times K plus on here, and you reduce, and you do the standard Hamiltonian reduction using momentum map and everything. There is no Poisson-Lie groups. You just do standard Poisson reduction here, and you should choose the almost the same conditions. So the conditions which he chose were almost the same, but they were the linear versions, right? So everything, this is Kazhdan, Kostan, Sternberg, this is a character, and this is just something. And he turned the handle, and he'd see what you get, and what you get is this result of Inozemtsev and Meshcheryakov. Then, because I'm in constant communication with Lotzi, and by the way, as I've mentioned, unfortunately, constant conflict, unfortunately, because I love him dearly, but I'm afraid that we do argue all the time. And we agreed that it would be interesting to extend this to find the Reisenauer's version. And I suggested, well, look, in fact, all we have to do is replace everything you see by the suitable Poisson-Lie group gadget, and the Poisson-Lie group gadgets everybody knows is to take the Heisenberg double of this. So take the Heisenberg double, and it turns out that the Heisenberg double is just exactly this, and this is the situation. This is the analog of the dual. This is the analog of G. So this is equal to G times G star. In this case, G is this K, and G star in Poisson-Lie group world, it corresponds to this. And I calculated and calculated, and in fact, I got this result in which Lotzi just ended up, he didn't want to get involved for some reason. It was just a horrible calculation. He didn't want to get involved. And that's what I did before I came to Moscow. I was in the whole of the summer before I came to Moscow. I found this thing, and I had a horrible system which didn't seem to be related to anything. You want it to look like a Reisenauer's type thing. Or this you expect to just be able to see it. When all of the examples people have done before, you just say, well, okay, I've got a thing that looks like Reisenauer's. Reisenauer's looks like cos p multiplied by v. Right, that's a general structure of this. Instead of saying p squared, half p squared plus v, Reisenauer's looks like this, and this should have some suitable many-body interpretation. So it looked a kind of like Reisenauer's, but not in the nice way. It didn't look like the obvious generalization of this BCN system that was here. And I sat here in Moscow for years and years, being frustrated and sometimes trying to do this. And when I first came to Moscow, and I had to listen to students solving problems, for example, in math analysis, first year students, and I couldn't imagine they were solving ridiculously difficult problems. I had, these fantastically clever students, one of these days, all I'll have to do is tell them my problems and they'll solve them for me. I mean, this is just, they are too clever. And in practice, this did not happen. But I did have some clever students who came to some lectures that I was giving on Poissonnier groups. And because they were nice and interesting, they stimulated me. And at a certain point, I had an insight myself. It's a trivial insight, Joseph. It's just a trivial. But after years and years of frustration, I made this obvious step, right? Because what is a Heisenberg double? A Heisenberg double is a generalization of the cotangent bundle. And the cotangent bundle is a special case of the Heisenberg double when you take the group. So the group there is SL. So this is just an example of Heisenberg double. But when you think of this as a group of G semi-direct product, G star. So you just have to bring in this picture of the semi-direct product there, and it shows you the way to do it. And when I did that, suddenly it all came out, and I understood what it was. And I published it in Communications in Mathematical Physics. It was a respected result. Then Lotzi got involved with it, discussed it with me, and he wanted to do a different project. So he actually solved it separately without me. He went and did this case. So now instead of SU and N, you're doing SU2N. And that's exactly what you've got here. So whereas I had FL2N and I factorized it as SUNN and SB, he took this and he factorized it as SU2N and B. And he did exactly this. And he published that together with his PhD student at the time. And then we were discussing, and he also, well, never mind, that's an important detail. So then we discussed this and we tried to understand how to get a dual pair, and we'd thought about it for years and we couldn't understand how to do it. And at a certain point, I mean, because I understand it looks like stupid nonsense, but there is this thing which I've cleaned now, this formula which involved, I mean, it was kind of like a key step. This thing where you take GG dagger minus GG dagger, whatever it was. I mean, that stupid thing that was I included it just because I just thought, well, it's funny. Everyone should know that. This was a key step, actually. And then we managed to get this. And, it all came out. So, I mean, you have some systems. The only names that you could give them are, I mean, they don't have any names. Sorry. But they are systems, they belong in the, as Lotzi said when I spoke to him the other day, he said, well, they allow you to get your bread and butter. They are results which are welcome in respectable journals. It's difficult to say much more about them than that. But people, I guess we all want to understand the things better. Actually, I have to say, I was especially grateful to this. I was very stressed by it because I understood that this is not even a recent result. But I was happy because just in preparing for this, it forced me to look at this again. And I realized that I do have something else that I should work on. So it will not be, and maybe I'll publish another respectable article on this. It will not be dramatic, but it's there is something else to be done, as I realized. So,
Okay, thanks a lot.
At least I got some benefit.
Can we
take everything off? Yes, yes.
I need. So thanks a lot. Questions, remarks?
Questions.
You have a question?
No.
No question, no remark? Okay, then thanks a lot again, indeed. Well, we have no program for the next time because I tried, but couldn't find anyone who wanted to make a talk, but let's hope. So thanks a lot, goodbye, and hopefully we shall meet Maybe not next week, but in 2 weeks, we'll see. Goodbye.
Thank you.